Alright guys, this is the rest of objective 1B. This is 1B2. 1B2 focuses strictly on the structure and function of enzymes. And so enzymes are a special class of proteins. These are your proteins that serve as biological catalysts. And because they are enzymes, that means that they are made up of amino acids, okay? Remember, proteins are amino acids. These are extensively folded proteins though. They go all the way up to at least the minimum of an enzyme is going to be that tertiary structure. Remember, proteins have 4 levels of folding. So you're going to go minimum tertiary with an enzyme. Some of them do go to quaternary, but you're going to have at least that subunit. And so that subunit is going to be folded so that it has this special area in it, and these special areas are called active sites, okay? And the active site is going to be where your substrate or your starting material is going to actually bond to the enzyme. Now, enzymes are biological catalysts, which means they speed up the rate of a chemical reaction by lowering the energy of activation. But they do not themselves participate in that chemical reaction. What enzymes do is provide a favorable location for the reaction to happen. So because they don't actually participate in the reaction, enzymes are unchanged in a chemical reaction. Now, so the way that works, if you look at this graph here, the way that works is any chemical reaction. So we're showing a chemical reaction here. This is going to be one where reactants are going to be turned into products and we're going to be releasing energy. So my reactants have a certain amount of energy, available energy, and my products have a certain amount of available energy. Enzymes don't change that, okay? The difference between the amount of energy that was available in the reactants is going to be the same as with or without an enzyme. It does not change that available energy. What it changes is the energy of activation. For any reaction to get going, that reaction must absorb energy from its surroundings, from its environment. And so that's called your energy or activation, or E sub A. So what an enzyme does in a catalyzed reaction, an enzyme lowers the amount of energy the reaction needs to get going so that it actually comes to completion or creates those products faster. So what we have here, the first line shows an uncatalyzed reaction, and look how much energy it has to absorb, versus a catalyzed reaction has to absorb less energy, so it starts going faster, so this reaction comes to completion sooner. So that's the only thing an enzyme does. It provides an environment which causes the reaction to need less energy to get started, and since it needs less to get started, it happens at a faster rate. Now, enzymes are proteins that are folded, and so they are sensitive for certain things. Specifically, they're going to be sensitive for pH, temperature, and salinity that can actually change their structure, but they're also sensitive for, they also respond to the concentration, all right? So that's going to be the concentration of enzyme versus substrate, because if there's no substrate, the enzyme can't do its job. If there's a whole bunch of substrate and very little enzyme, then the rate's going to be slower than if there's a lot of enzyme. So there is a ratio of substrate to enzyme that makes that reaction move at a steady rate. Now, your enzymes, again, are extensively folded proteins. They fold so that they have an active site. So not only are they specific for their pH, their temperature, and their salinity, which is the percentage of salt in the solution, they are also specific for which substrates they work with. So this active site is going to have a specific shape, which will allow only certain substrates to bind to it. If the substrate does not have the correct structure, it cannot bind to that enzyme. So we call this often a lock and key format, whereas the key must fit the lock, okay? You can't just put any substrate into any enzymes. So for example, when you're naming enzymes, their name tends to tell you, let's take something like milk sugar, which is lactose, ends in ose, so I know it's a carbohydrate or a sugar. The enzyme that is going to be able to work on lactose or provides an environment for lactose is going to be called lactase. Remember I said digestive enzymes tend to end with ACE when we talked about the macromolecules. So lactose is going to be bind to lactase. But if this was sucrase, which is a different enzyme, lactose would not be able to bind to the active site of that. Now, substrates are your starting materials, and the substrate is going to bind to the active site of the enzyme, forming what's called an enzyme substrate complex. When it loosely binds to the enzyme, whatever type of reaction, if this is a digestive reaction where things are going to be broken apart, you're going to have hydrolysis where water is going to be going across the bond. If this is a synthesis reaction where you're going to be putting things together, which is like what I'm showing you, you're going to have dehydration or condensation, which means water is going to be coming out, okay? So when this happens, what's going to be released from the enzyme is going to be the product. Remember, lines represent bonds. Notice here they went in, they weren't bonded together, but over here they came out and they are bonded together. So now these two substrates have formed a bond, and so they're no longer individual substrates, they're now a new product. And so your product is going to be your ending material. So the structure of the enzyme, though, remains unchanged because the enzyme does not participate in this chemical reaction. Now, oftentimes on a graph, you'll see the enzyme activity represented. I'm showing pH here, which I forgot to label my graph because we want a properly labeled graph. So I'm looking at the effects of pH on enzyme activity. So I have enzyme activity here, have the effect of pH here, and notice that on my graph, my enzyme does not start working until it gets above like a pH of 4. So any activity indicates the enzyme is working. It works best between this range, somewhere between 6 and 9 is what's going to work best. And as I begin to increase my pH, notice my enzyme activity falls off until ultimately it stops working. So what this means is this enzyme works within a range, but it also has an optimum range. And that optimum range is where we're going to see that highest enzyme activity is where it's going to work best. If I was looking at this in a table, it may be where I see the most amount of product. Because if their enzyme is producing product at a higher rate, we're going to see a higher level of product being produced. Versus if there's no product, then the enzyme is not working. Or if there's less product, the enzyme is not working in its best environment. All right, guys, that's it. Toodles.